Hey, everybody. So there was a question that came up in the Rhizomic sequencing Discord, which is my Discord server, that I thought was really interesting and I wanted to talk a little bit about because it brings up a kind of way of thinking about the timing signals that is different from the way that I usually talk about them. And I think that will make sense as I get deeper into this. But it all starts from this user Girk, who says they've been trying to make a signal-based sequencer where they use three lists: notes, note lengths, and velocities. And that's working great, but they want to introduce some swing and groove into the sequence by running the phasor through something like rtt.feel. And they have their patch here. And so we have a phasor and then a subdiv. And basically the kind of phasor system isn't doing very much, because what we're really just doing is getting events from subdiv. So every half of this phasor, we get an event, and kind of downstream here, basically what happens, the magic is really down here, where a note value, which will be something like a quarter note or a half note or a dotted eighth note, in Max's kind of special syntax for that, gets passed in here, and it basically triggers that note, and then when it's time to trigger the next note, it triggers the next one. So it's a very different way of thinking about a rhythmic pattern from the way that I've often talked about it, where very often I'm talking about it in terms of, okay, we're going to create a clock, which is based on some phasor, and we're gonna then subdivide that into basically equal slices. And then the generation of the rhythm might come from omitting some of those subdivision slices. There are other cases like the nested tuplets case where we irregularly subdivide. And that's a little bit more similar to this type of approach that we have here in this patch, but it's also a little bit different. So I'm going to go into Max and just get into a little bit of, okay, how do we think about how this works? How can we use it sort of in conjunction with a system that still uses a phasor as the initial source of time? And then also, how does something like swing or any kind of groove factor into a system like this? So I have a patch here that gets into it, but first I'm going to just go back to basics really quickly. So, right, we normally talk about this idea of we have a phasor and then we have a subdivision. And I can create a couple of live.scopes here. And then if I have a subdivision of, let's say, 4, then I'm dividing this smaller this phasor into 4 segments, right? And what Girk here wants to be able to do is they basically want to be able to specify like a list of these time values. So like a half note, which in Max is 2n, a quarter note. We could do like I don't know, an eighth note triplet or an eighth or a dotted eighth note. So this is sort of a Max specific way of notating the types of common note lengths that you would see in typical musical notation. So notes and dotted notes and triplets. So if I were to basically say, okay, I have this list, I want to basically now have ramps that are one that's a half note long, then one that's a quarter note, then one that's a dotted eighth note triplet long, then one that's an eighth note triplet, then one that's a dotted eighth note triplet. So it's not an irregular or not a regular subdivision, it's an irregular subdivision. So that's the objective here. Let's talk about some ways that we can do it. So we'll start with this first example, which is using the line object. And in fact, actually, you could also use delay, but you won't get a phasor out of it. So I'm going to use line, which is going to give us a ramp. So what we do here is we just pass in some list of these note values, And then we have ZLReg here, which is going to store that list, right? So when I send that list in, it comes out here and it gets stored in the ZLReg. And then in the beginning, I need to just kind of initialize the system. So I'll initially bang and kind of start the system. And now it's already running. And what basically happens is each time we have when we initially start it, we get a bang. We pass through the list from ZLReg. And then we go into ZLRotate, which is just going to rotate it initially by 1. Well, initially by 0, and then by 1, and then by 2, so that we're kind of like, we're rotating the list around. And hopefully, if you just watch this carefully, you can see what's happening. So that each time we get a new event, we shift one step over within the list, and we generate a ramp of that length. And with line, that's easy to do. We just send this message 0, 0 to tell the line object to go immediately to 0, then 1 and the amount of time that we want it to take to get to that destination. And with line, we can pass directly in these note values. We don't have to convert it to milliseconds or anything because line understands that as long as we have a transport in the patch, which we do over here. The line object gives us a bang when it's finished with its ramp. And so that's the way that we basically perform this kind of advancing or rotating of the list by each time passing -1 into this simple accumulator here. So that basically we kind of have a running process that is keeping track of how many rotations or how many steps of rotation in the leftward direction, that's why we're using a negative number, should be used in this original input list. And as you can see, ZLRotate is pretty smart. It doesn't care if we go way outside of the bounds of the length of the list. So I'm just continually accumulating, negative values. And this will get very high if this goes for a long time, but that's totally fine. We're just going to keep looping around that list and generating the ramps at those different intervals. Okay, so that's a cool approach. It does rely upon signal to event conversion, right? There's no way that we can kind of have this entire system work in the signal domain because, we need to send a message to line. It's the only way that you can trigger it. But also because we need to kind of look up something in the list when this process is done. So we have a sort of feedback path here. And so if you're in MSP, if you want to have any kind of feedback path like this where the input to a process is affected by the output of that same process, then you basically need to convert to max events. If you want to keep everything fully in the signal domain, which, you might want to do because you like the sort of elegance of it, which I admit that I do, but it's certainly not necessary for many applications, then you would really want to work in Gen. So that's what we'll get into next. So this version, we're looking over here now, is a little bit more complex, and there's a few reasons for that. Number one, we can't use just these time syntaxes by themselves. We need to basically think about them in terms of a subdivision, in terms of some sort of a scaling of the slope of the input phasor, which we can see here. So that's the first thing. We need to perform a conversion from this format into a subdivision. The second one is that passing a list into Gen is not as obvious as passing a list into max patch like this. So we'll talk about both of those things, and those are really both being handled over here. So we have this abstraction note to subdiv, which we can take a look at, where basically what's happening is we're iterating over the list. We're using some regular expression to try to figure out if it's a dotted note or a triplet. This is actually, so to give you a quick overview of the regular expression here, This is looking for the number part, so 2 or 4 or 8 or whatever. This is looking for the n, which is basically always going to be there. And then this is checking to see if there's a d or a t. And then we reverse that around. What we're going to get from the second outlet here is a list of the different items. So if we put in, let's say 8n, then we'll get, I think, just 8 actually, because it's only going to give us the ones that are inside the parentheses. If I put 8nd, which would be the dotted note, then we'll get, after performing this reversal, d followed by 8, right? And so this is the way of basically figuring out, okay, well, what is the base subdivision, 4, 2, 8, 16, whatever, and then is it a triplet or is it dotted? If it's dotted, then we're going to multiply that value 8 by 2/3. If it's triplet, then we'll multiply it by 1.5. If neither is there, then we're just going to pass it through. I found that it actually behaves a little bit strangely. This is still a list, even if I just passed 8n, it's still a list, but it just has like a kind of like an empty value actually, but a little bit strange. So I found you had to put a zeal nth2 in here to extract that second item, which is the actual number. And then we pack it back into a list in zeal group and bang it out. So we get a new list that looks like this, which is actually the subdivisions of the input phasor, assuming that the input phasor is 1 bar, right? We then put that into a buffer, and that used to be a lot harder than it is now. We can now use this array.toBuffer, which is really handy. So we just tell it what buffer we want to put the numbers into, and then it's nice here to also specify resize1, which will automatically change the number of samples in the buffer to fit our data, which is really, really handy, because otherwise you need to kind of keep track of, well, how long is the data, so that when you perform the lookup over here inside gen, which we'll look at in a second, you have to keep track of that so that you don't try to read something that you shouldn't read. But because we're resizing, we can actually just tell gen, hey, just read from the whole buffer, because the buffer's length is always going to be exactly the same length as the data that we care about. So that's great. And then I'm just plotting that same data here. So if we now go into the playback patch. So like I said, we're not able to work directly with the time values. We have to work just with subdivisions. So what we do essentially at a high level, and I'll get into more of the details, but if we just are trying to look at this patch as a sort of a general structure, we take the phasor and we immediately take the delta, and then we perform this wrap -0.5, 0.5, which comes from Go, which the output of this we can think of as being kind of a number that just represents the clock speed. So rather than the whole phasor itself, where the value is this kind of phase, like where are we within the unit of time, instead that this value is just how fast is the time flowing. In other words, it's the slope of the line. And then we just multiply that by one of these subdivision amounts that we have over here. And we build a new phasor. So that's what all of this is. We're just accumulating again to build a new phasor, and then send that to the output. And then we have a section here that detects the end of each of those subdivided phasors. And each time that happens, we advance a little counter, which is living inside of this history that's called index, which is then used to look up the next subdivision in the list. So very similar to what we have here, where we're kind of advancing a little counter down here, and we're going backwards because that's what ZL-rot needs. So a little bit of an implementation detail there, but the basic idea is, like, each time a ramp is done, we say, let's advance one more value, and use that then to look up the next item in the list. Same idea here with this delta and less than 0, we can get basically an impulse when this subdivided ramp that we've built is complete. We can advance our little counter, and then we can use that counter value to look up the next subdivision. There's then a few additional details here. So one is we can just hard reset the pattern back to the beginning if we want by sending an impulse into the second inlet of the patch. And that's what this switch here does. This question mark object is a way to basically, if there's an impulse here, so if the condition at the first inlet is true, meaning the value is non-zero, then it's going to take the value at the second inlet, which is disconnected, so it's 0. Otherwise, it will take whatever's at the third inlet. So in its default state, it's just continually counting, and just accumulating, adding to a running total of what's flowing through this third inlet and to the outlet. But anytime we send an impulse into this first inlet, we're going to just jam a 0 in there and restart the counting. And the same thing is happening here. So this is the same type of circuit here that we have here. To be really accurate for you, it's like this part, which is just an accumulator, just an adding to a running total. The difference is that here we're adding a stream of pulses, which allows us to get a counter 1, 2, 3, 4, 5. Whereas here we're adding up a very small number, which is this clock speed or phasor slope that we've scaled by the subdivisions. And so here we're building something that looks a lot more like a ramp to us, whereas here, and the range of this ramp is from 0 to 1, whereas here we're looking at something that looks a lot more like a stair step from one integer to the next. The reason that we insert the switch here with this question mark is to be able to have this kind of hard sync, so that if basically the subdivision is if the subdivisions don't add up, so that they will complete at the same time that the phasor does, we basically force the current subdivision to complete early when the phasor resets. So I'll show you that. So let's use an example where we have like 2 and 3. So I'm just going to bypass this whole part and just pass subdivisions indirectly. So now we have that. And you can see if I line up the phasor, the input phasor and the output ones, that they aren't synced up at all. So when this one finishes, these guys are completely like out of sync. If we wanted to force them to remain in sync, we could enable the hard sync. And you'll see that what happens is anytime this lower one, which is really the first one, so I'll switch these around. Anytime this upper one now resets, it force hard syncs the lower one. So because you may care about this kind of unit of time. Maybe you don't, but if you do, then you might want to enable that. The last thing that I'll talk about is just another advance upon this concept of the syncing, which was kind of a follow-up question actually from Girk, who had a really nice diagram. I gotta say, Girk, I commend you for like asking questions very clearly. I appreciate that. So here we have this example where this is the original phasor. This is the one that's going to get truncated. But what Girk was saying was, I actually want this. So this last one, all these other ones are the same. The first 3 are the same, but the last one actually has a different slope. It's much steeper in order to kind of make itself fit in here. So I'll show you how we can do that. So that's on a separate tab. So it's the same patch. The only difference is that basically, if we're in the smart sync mode, so I changed this from kind of a hard sync toggle to a different parameter called sync mode, where we still have the off, no sync. We still have the hard sync like I showed you before, so we can see that in action. And then there's this new mode called smart. And the way that we achieve this is basically anytime there's a new subdivision that arrives, we check to see, is there going to be enough time for this subdivision to happen? And if there isn't, we use basically what there is enough time for, right? So we kind of use the the minimum possible subdivision at that point. So this patch is the same as the other one. I just copied it and augmented it. And the places in which it's augmented are, so over here, this hard sync stuff is exactly the same. I just had it patched slightly differently just to be able to manage this new parameter that has 3 options rather than only 2. So if we're in hard sync mode, it works totally the same. But this is where we add in, let me be really clear here. This is where we add in new stuff to account for the sync mode 3 or 2 rather, which is the hard sync. So the idea is, when we get a new index, we use the change object to just detect that there's a new one. So this is basically us detecting that the last subdivision has completed and it's time to get a new value. And we're going to use that to latch the Phasor's value at that current time. Because what we want to do is basically get a new subdivision value that we're going to then use for the duration of the next period. So we just grab the current Phasor value, we subtract 1, or we subtract it from 1, and then we take 1 over that. And what this is then going to give us is what's the minimum legal subdivision. So to give you an example, if we have this impulse here occur when the Phasor is at 0.75, then we say 1 minus 0.75 is 0.25. Then we take 1 over 0.25, which is 4. And so that tells us the minimum subdivision of this Phasor that you have time to execute before this Phasor completes is a subdivision of 4. Okay. And if sync mode 2 is, if sync mode is set to the value of 2, so we're on that smart mode, then we pass through what that minimum legal subdivision is, and then we take the maximum between that value and the divisions. And the max and min can be kind of confusing because what we want to take is whichever is higher between the two, because we're subdividing, right? So a higher value is a shorter amount of time. So if this value, if, to go back to our example, if we the lowest subdivision that we can execute is 4, and we get an 8 here, then it's fine. We'll just take the 8 and do that. And then when that's done, then we'll do that process again. And this is going to tell us you got a subdivision of 8 time remaining. And then if, let's say at this point, the next item in the list is 2, then there's not going to be enough time for that. So we'll do another 8 because that's what this said the kind of minimum time remaining is. But besides that, it's the same patch, right? We do the same thing of scaling the slope, same accumulator here, nothing changed here. All we really did was just insert a whole section that allowed us, when sync mode 2 is enabled, to identify how much time is remaining, what therefore the minimum legal subdivision is, and then take the maximum between the subdivision from the list and the subdivision, that minimum legal one. Okay, so I know that this one was a little bit more of a kind of a theory video, no musical examples. But hopefully for those of you that are kind of already deep down the rabbit hole on this stuff and thinking about, all right, what are the different ways in which I can, construct rhythmic patterns, this is useful. The last thing actually that I should have said earlier and forgot to say is this question of, okay, well, but then how would I get a groove in here? How do I get a swing if I want to use rtt.feel? Well, that can just go right here, right? Because the nice thing about this system is that we're still using the Phasor as our kind of main originating source of time. And when I think about the idea of a swing, I always think about it in terms of this kind of warping of the clock that precedes the musical events that you're going to generate from that clock, right? Rather than thinking about swing, like if we think about kind of classic jazz eighth note swing, rather than thinking about it like, oh, the drummer is hitting the cymbal later. Instead, the way that I think is more useful to think about it is that the feel of time that all of the musicians in the band are using has this kind of undulation to it where it slows down and speeds up over the course of the bar. So following that same concept, we would basically just insert rtt.feel or whatever object we would use to modulate time, quote unquote, into the patch at this stage, and then you can everything else downstream basically inherits from that time modulation that you perform. Of course, if you wanted to do it, upon these subdivisions, because you were going to subdivide further downstream, you could do that as well, right? Because one of the sort of beautiful things about this kind of construction of a timing system is that we have a ramp go in and we get a ramp out. So this, can be converted into an impulse that just generates a musical note that we send off via MIDI or whatever. But we can also think about this just as another kind of cell of time that we then further subdivide, which can be quite useful in a lot of, I think, performance or compositional contexts where you might want to trigger a note, but then actually have another pattern that kind of occurs within the duration of that note, or that just begins in sync with the beginning of that note. So we can think about the music as kind of having these really nice synchronous relationships between the different elements. And we really achieve that by building a kind of rhythm hierarchy that starts at the top and goes downward based upon subdivisions. So I would say that while I started the video with, hey, this is a different way to think about, timing, it's really just a modification upon the themes that we've already been talking about. And the only modification is the subdivisions aren't regular, they're irregular. And we just basically modify the subdivision each time a subdivided ramp occurs, we just change what we're subdividing by. But besides that, it's exactly the same system as the kind of more standard one with the subdiv object. All right, that's that. Let me know if you have any questions. I will see you next time. Thanks.